Hi, this is Mrs. Kidman, and in this video, we are going to be discussing how we can prove that triangles are similar. So what we want to know is, in the last video, we talked about how to show that things are similar, that all the sides have to be proportional and all the angles are congruent. But do we have to do that every time we have two triangles and we want to know if they're similar? In fact, we don't. So what we can do is there's actually three different things that we can look for. Similar to how with triangles, we can prove that they are congruent as long as we have a side angle side that are congruent, or a angle side angle, things like that. You know how we have those triangle congruence theorems that tell us instead of having to know all the sides and all the angles are congruent, what we can do is we can actually limit ourselves. And based on those, we can show that the two triangles are similar, just like we could with those congruent statements. So let's talk about what those ways are. Well, there are actually three ways that we can prove two triangles are similar. One is by the Angle-Angle Similarity Theorem, which basically says that if two angles are similar, all three angles are similar, therefore the triangles are similar. By the Side-Side-Side Similarity Theorem and by the Side-Angle-Side Similarity Theorem. So we're going to take a look at each of these three different theorems and then use them to show that triangles are similar. So let's take a look at this first one here, Angle-Angle Similarity Theorem. If two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. Now, why is this the case? Well, I want you to think about this. Let's draw a picture. So I have two triangles here, 1, 2, and I'm trying to decide if they're similar. Well, if I know that these two angles are the same and these two angles are the same, guess what? Because I know that the sum of the interior angles add to 180. If these two angles are the same and these two angles are the same, these two have to be the same because there's only three angles. And if two of them add up to the same thing, the third one does as well. So we know that that works. Now, how does this prove that two triangles are similar? Well, by the time that the angles are all put in, it actually constricts our triangle as to what it can be. Sides can be proportionally whatever they want to be, but those angles actually restrict the proportions to make them exactly the same. Because if a side is disproportional, the angle in turn also has to be disproportional. Now let's take a look at a couple of examples of this. So we want to determine whether or not these triangles are similar, and if they are, write a similarity statement. Now a similarity statement is one of those ones where we say the triangle ABC is similar to triangle DEF, something like that. Okay, so let's take a look at these two triangles and show whether or not they're similar, and then use a statement to back it up. So we are given two angles here. Now we know that these two are both 90 because they're right angles. But then we were told that these other two, one was 26 and one was 64. Well, what parts of these triangles are congruent? Well, D is the same as G, E is the same as H, and C is the same as K. So how can we show that H is the same as E and C is the same as K? Well, we can actually solve for this third angle by knowing the other two. So we know that they add up to 180. So 90 plus 64 plus something needs to equal 180. Well, let's look at the math there. If we combine 90 plus 64, what we end up getting is 154. So we get 180 is 154 plus x. Well, to get x all by itself, I can subtract that 154 from both sides. And what we end up getting is 26 equals x. Okay, so that just showed us that this is 26. By a similar process, we can actually show that this one is 64. And therefore, all the angles are the same. But do we have to make that one 64? No. Why? Well, by that angle-angle similarity theorem, because we have two that are 26 and two that are 90, it forces that other one to be 64. Therefore, triangle CDE is similar to triangle KGH by the angle-angle similarity theorem. Fantastic. So that's kind of how we would do it. Now, this next example here is very similar. We want to show that these two triangles are similar. Now, these ones take a little bit of a different approach than that previous one. So in this first one here, we've got triangle ABE, which is this little triangle. And we want to show that it's the same as triangle ACD, which is this big triangle here. So we want to show that those are the same. Now, how can we show that those are the same? Well, think of it this way. Angle B is congruent to angle C, right? And we know that those are congruent to one another because they both are in that same place. They're the corresponding angles. I also know that angle A is the same as angle A. Well, why is it the same? because it's the same. It's by that symmetric property of equality. Anything is equal to itself, or anything is congruent to itself. So we prove that those two angles are the same. So if we know those angles are the same and this angle is the same in both, then that implies that angle E has to be the same as angle D, because the interior angles have to add up to 180. So if the other two are the same, that one's the same. Therefore, by angle similarity theorem, we know that triangle ABE is similar to triangle ACD. Notice how I didn't make you do a formal proof, but we want to talk about some of those reasons. Now, this next one is a little interesting because it talks about how triangle SVR, which is this one here, is similar to this one here. Now, how can we show that those two are similar? Well, guess what? These two lines here are labeled that they're parallel. So we know a couple of things. We know that this angle and this angle are the same. Why? Well, because they are vertical angles, and vertical angles are always the same. And then this line here, this PT, actually acts as a transversal. So because that acts as a transversal, we know that this angle has to be the same as this angle because they are alternate interior angles. And what do we know about those? Well, they're the same. So we've proven that angle V is the same as angle V because, yeah, angle V is the same as angle V because they are vertical angles. We've proven that angle P is the same as angle T because they are alternate interior angles. Therefore, by the angle-angle similarity theorem, we know that those two triangles, SVR, is similar to triangle UVT. Bam, isn't that awesome? Okay, so let's kind of move on. We can use the same idea here when we're talking about looking at people. So this woman looks at a flagpole and it's casting this shadow that's been measured here. And we can see that it casts its own shadow. We're not going to draw it this way. So she's looking up at it and she notices that this flagpole casts a shadow. Similarly, she's standing there and she casts her own shadow. How tall is the flagpole? Well, guess what? We can use this idea to figure out how tall they are by looking at these angles. Well, this angle has to be the same. We know these two are the same, so how can we figure that out? Well, really what we want to ask ourselves is, can I figure this out? Well, if we can show those triangles are similar, then we can. But let's move on here. Let's talk about other ways to show that triangles are similar. Another theorem that we can use is the side-side-side similarity theorem, which says if the corresponding side lengths of two triangles are proportional, then the triangles are similar. Why? Well, we know that if all three sides of a triangle are congruent to all three sides of another one, that means that their angle measurements are the same. And the reason why is because once you have the sides locked into place, the angles can't change without changing the sides. Right? Once we have two angles or two sides with an angle inclusive, it really affects it. And we can kind of explore this using different manipulatives as we need to. But as we see that, if they're proportional, similarly, then the triangles have to be similar because those angles have to be the same, just like with that other one. So let's take a look at this example. Are either this one, triangle 1, DEF, or triangle 2, GHJ, similar to ABC? Well, let's take a look. What we can do is we can actually look at the different side lengths and see if their sides are proportional. If they are, then they're similar. If they're not, then they're not similar. So we're going to look, notice how they labeled them in colors. So those ones are similar. So I'm going to start with our original one our new one on top. So I've got 6/8 should be equal to 9/12, which should be equal to 12/16. Okay, so let's take a look. 6/8 simplifies into 3/4. 9/12 simplifies into 3/4, and 12/16 simplifies into 3/4. So bum, DEF does work. Now, what about this other side here? Well, we've got an 8 and an 8. Okay, and then we've got a 10 and a 12, and then we've got a 16 and a 16. Well, the two 16s equal 1, these 8s equal 1, but this one actually equals 5/6. So this one is not proportional, therefore they cannot be similar. So that's kind of how we can use that side to determine it. Let's take a look at one last example here. So find the value of x that makes these two things similar. So that means they need to be proportional. Well, because they have to be proportional, we know that those corresponding sides need to have the same ratio. So I'm going to look at this. We've got a 12:4 with this ED to BC to BA, and that should be the same as the 18 over x minus 1, which should be the same as the 3 times x plus 1 over 8. Now we know that these proportions all have to be the same, and guess what? They all need to equal 3. So we have a couple different ways of doing this. One thing I'm going to do is just set each of those equal to 3 and solve for x. And we don't actually have to do it with both. We just have to do it with one. So I'm going to do it with this one here. So I've got 3x plus 1 over 8 equals 3. I'm going to multiply by 8 on both sides to get rid of this denominator. And I get 3 times x plus 1 equals 24. Then I'm going to divide both sides by 3. And I get x plus 1 equals 8. Subtract 1 from both sides, and we end up getting that x equals 7. So in order to put x in that makes it 7, that should make it proportional. Well, here, if we put x in at 7, that would make this 24 over 8, which is the same as 3, which works. Now let's check this one. We've got 18 over 7 minus 1, or 18 over 6, which also equals 3. So 7 is that magical number. Now the last theorem that we're going to look at is the Side-Angle-Side Similarity Theorem. And in the Side-Angle-Side Similarity Theorem, it says if two sides of one triangle are proportional to the two sides of the other triangle and the included angle is congruent, then the triangles are similar. Now why does this work? Well, let's take a look at this triangle here. So I've got a triangle. It looks like this. And another one that looks like this, and we want to know if they're similar. Well, I say that these two are the same, and these two are the same. Or not the same, but they're similar. So I guess they're proportional there. Let's pick a proportion. So I'm going to draw a new triangle. So we've got this one, I'm going to say this one is a 2, 3, or not a 2, 3. Let's make this one a 3, 4. And make this one a 6, 8. And then we also are told that this angle here is the same. Well, guess what? By having those two sides there, we know that if all three sides are the same, then that they have to be similar. We also know if the angles are all the same, that it has to be similar. Well, when these two sides with their proportions end up with this angle, that angle locks it into place. It can't, those sides can't move anymore. And so we are really looking at the distance between this point here and this point here, and this point here, and this point here. Now, because that angle locked them into place, this one has been extended out over here like this, but that doesn't change that proportion of it because it's still opposite that angle. And you can kind of see as you look at that those sides really lock it in. So we can use this as well to prove it. Now, if you want to prove this theorem, you're more than welcome to. I will not be doing it in this video, but that is something to look into. So what we want to do in this example is explain how to show that the indicated triangles are similar. Well, we've got a couple different ways that we can do that. In this case, we can look to make sure the sides are proportional. So let's say 24 over 18 needs to be the same as 28 over 21. Well, 7 goes into both of these, so that's 4/3. 6 goes into both of these, and that's 4/3. So the sides are proportional, so the angles are the same. So by the Side-Angle-Side Similarity Theorem, they're congruent. We can do the same thing here. So this angle is there, this angle is here. The triangles we're comparing are YZX, which is this little triangle, to ZXW, which is this bigger triangle. So we're actually comparing those two. So we have this angle here, because that one's 90, it's supplementary. So this one also has to be 90. And so that means the sides we're comparing are this 9 with this 16, and this 12 with this 12. We know that 12 and 12 are actually going to be the same. So we know this is also 12. So we've got our two triangles here. And this is a 90-degree angle, so we can compare this leg. We're not actually going to compare it to this one, though. What we want to do is, because these are the same, notice how these create right triangles. So we have a leg, a hypotenuse, a leg, a hypotenuse. I'm actually going to use these two legs to look at it. And I'm going to compare, because this one's the hypotenuse and this one's the hypotenuse, they're both opposite. This is not actually going to be compared to that. It's going to be compared to the 9, because notice how we've got a short to this triangle, which is the long to that triangle, but the short to this other triangle. So we want to compare the short sides to the short sides, the long sides to the long sides. So we've got a 12 over 9 should be the same as a 16 over 12. And we know that that's 12 based on this, and that becomes a 4/3. This one becomes a 4/3. Those sides are proportional. Those angles are proportional. So if the legs are proportional of a right triangle, we can also, and the right angle is proportional, then we know that those triangles are proportional by that side angle side. Okay, let's take a look at one last example here. You're building a lean-to shelter starting from a tree branch as shown. Can you construct the right end so it's similar to the left end using angle measures and side lengths shown? So let's decide if we can make a similar triangle on this end as we do on this end based on what we have given. So we are given that this is 53 degrees. We've got a 10, a 15, a 9, and a 6. So this side should be similar to this side. Our angles are the same, and this side should be similar to this side. Let's check to see if they are. So 9/6 should be the same as 15/10. Well, 3 goes into both of these, which will simplify us into 3 halves. 5 goes into both of those, which is 3 halves. So yes, we can construct one on the right end, so it's similar to the left end, based on that angle measurement and length shown, because by that side angle side similarity theorem, we end up getting 2 triangles that are similar to one another, which means it can be done. If you have any questions about proving that 2 triangles are similar using these 3 different theorems, feel free to ask. But again, we've got 3 theorems here that we can use. We can show that 2 angles are similar, 2 angles are congruent, meaning the triangles are similar. If we prove that all 3 sides are proportional, then the triangles are similar. Or if we prove that 2 of the sides are proportional and the included angle is congruent to the ones on the other triangle, then it also proves that they're similar. If you have any questions, feel free to reach out, but that's how we can prove 2 triangles are similar without having to do all of